For decades, artificial intelligence relied almost exclusively on text inputs to interact with users. Today, we are crossing a new frontier where machines can see, hear, and interpret the physical world just as humans do. Multimodal AI fuses computer vision, audio processing, and natural language into a single real-time perceptual framework. Traditional systems operate with siloed perceptions, running separate speech recognizers, visual object detectors, and text-based reasoners. This fragmented approach leads to significant latency, high integration costs, and lost contextual nuances. Multimodal AI breaks down these functional barriers, uniting separate signals into a cohesive, native understanding of reality. A single native multimodal model processes video, high-fidelity audio, and natural language simultaneously in real time. It correlates vocal tones, facial expressions, physical gestures, and spoken words seamlessly, mirroring the human brain's natural ability to integrate multiple sensory inputs into a single coherent picture of our surroundings. The foundation of a multimodal system relies on a shared tokenization space. Special visual and auditory encoders convert raw pixels and audio spectrograms into discrete tokens, mapping them into the same dimensional space as text tokens. This allows a single transformer model to process visual, auditory, and textual concepts together. The architecture is structured to support native cross-modal processing. Multimodal inputs pass through specialized front-end encoders and are projected into a unified latent representation. A central transformer network then performs multi-head attention across all tokens, enabling the model to learn complex relationships between sight, sound, and text. Reality is converted into a structured language that machines can compute. Video frames are decomposed into spatiotemporal patches, while continuous audio signals are tokenized into spectral frames. These distinct tokens are aligned temporally, allowing the model to understand how visual motion, environmental sounds, and spoken statements are connected. Multimodal AI is designed to process continuous streams of inputs with extremely low latency. Rather than waiting for entire files to upload, the model updates its internal state incrementally, resembling how the human brain processes sensory inputs, enabling fluid, real-time conversations and immediate contextual awareness. Consider a maintenance engineer pointing a mobile camera at a malfunctioning industrial turbine. The AI observes the visual cracks, listens to the abnormal operational hum, and reads the technical queries. It processes these three modalities in parallel to diagnose the problem and explain the step-by-step repair process immediately. The Fusion engine dynamically weights sensory inputs using cross-modal attention based on real-time environmental context. If a user is speaking in a noisy factory, the model automatically increases the weight of visual signals like lip movements and gestures, ensuring reliable performance in challenging real-world conditions. Training multimodal models requires petabyte-scale datasets containing paired visual, audio, and textual information. The model is trained to predict missing frames, align audio transcripts with visual events, and perform contrastive learning, establishing a shared semantic space where a picture, a sound, and a word share the same meaning. Processing massive real-time streams of video and audio requires high-performance hardware and custom network architectures. Specialized GPU clusters, high-throughput streaming protocols, and edge inference servers are deployed to handle the high token volume, ensuring low latency responses and maintaining a responsive user experience globally. As AI moves beyond text, standard benchmarks must evolve to test visual and auditory reasoning. Evaluation frameworks measure how effectively models perform tasks like visual question answering, document parsing, and speech emotion detection. Success is measured by how naturally the system interacts with complex physical environments. Adopting multimodal capabilities is simplified through standardized API endpoints and software developer kits. Developers can stream video and audio directly from mobile devices or browsers to cloud models, receiving structured textual responses and actions with minimal boilerplate integration code, accelerating product development cycles. Autonomous agents utilize multimodal capabilities to perceive, reason, and act in the physical world. These agents can monitor patient health in hospitals, inspect product quality on manufacturing assembly lines, and automatically log maintenance reports, closing the loop between real-world perception and software execution. The business value of multimodal AI lies in bridging the gap between raw physical events and digital decision-making. By automating visual and auditory inspection, organizations can identify operational issues early, reduce maintenance downtime, and unlock valuable insights from previously unmined video and audio datasets. Enterprises gain planetary scale, real-time visual and auditory awareness by deploying multimodal models across their operations. A single system can monitor safety compliance across multiple construction sites, coordinate logistics at warehouses, and manage customer interactions, transforming how organizations respond to physical events. Our physical environments are becoming responsive and context-aware. Smart workspaces, retail environments, and modern vehicles use embedded sensors and multimodal AI to adapt to human presence. This creates interfaces that feel natural, predicting user needs based on visual context, voice commands, and spatial behavior. The traditional keyboard and mouse interface is slowly giving way to ambient, multimodal interactions. Users can interact with technology using natural speech, eye gaze, hand gestures, and context. The system adapts to the human's preferred communication style, making technology more accessible and intuitive. Deploying visual and auditory sensors requires strict adherence to privacy and safety standards. Multimodal systems must prioritize on-device edge processing, data minimization, and secure audit logs. Ensuring user consent and maintaining transparency is critical to building public trust in ambient intelligence systems. Multimodal AI is the next computing platform, representing a shift in how machines interact with human civilization. By seeing, hearing, and acting natively in the physical world, AI becomes a collaborative partner. The era of text-bound interfaces is over. Welcome to the sensory dawn.